Sir, shall we start, sir?
Yes, sir.
Yeah. Very good afternoon to one and all gathered here. I hope everyone had a lunch. And once again, I'd like to welcome all the participants for a DPT-sponsored one-day online seminar on biotechnological applications using fiber optic sensors, organizing by Department of Electronics and Communication Engineering of Kongunadu College of Engineering and Technology. It's my glad to invite our session to resource person Dr. N. INR, Assistant Professor, Department of Electronics and Communication Engineering, Tyagaraja College of Engineering, Madurai. Welcome you, sir.
Yes, sir.
Before moving to session, let me see the short intro about our resource person. For that, I like to call upon Ms. K. Dharani from Final ECE to give away the intro.
Good afternoon, everyone. Knowledge is like a garden. If it is not cultivated, it cannot be harvested. I feel privileged to invite and introduce our resource person who is going to cultivate more knowledge. Dr. N. INR, Assistant Professor, Tyagarajar College of Engineering, Madurai, have completed PhD from NIT Trichy on fiber optics and phonetics, ME from Alagappa Chettiar Government College of Engineering on Optical Communication, and completed his undergraduate degree from Nalasu Sarathi Institute of Technology under Department of ECE. He published more than 20 journals and attended more than 20 conferences, seminars, and workshops. He delivered lectures on recent advancement in photonic devices and their applications. I hope you will gain a great knowledge at the end of the session. Now I call upon Dr. N. Ayana to share his thoughts with us.
Thank you. Shall I start, sir?
Yes, sir.
Yes,
Thank
sir,
you.
you
Thank
can
you.
start your presentation, sir.
Thank you. Thank you. Very good afternoon to all. First of all, I thank to organized team for giving me a wonderful opportunity to present the topic of optical fiber-based biosensors. One second, first share my PPT. Can you see my PPT?
Yes, sir, it's visible.
Yeah. Today, I am going to discuss about biosensors in photonic crystal fibers and its applications and principles. These are my outlines. And before enter to the applications and the principles of photonic crystal fiber, now I would like to discuss about what is meant by biosensors. And then what is the functional block diagram of the optical fiber sensors and the numerical techniques of the optical fiber sensor, and then listed some different types of optical fiber sensor based photonic crystal fibers like cancer sensors, hemoglobin, glucose, plasma, reconfigurable surface plasmon resonance based reflective index sensors and bending sensors. Yes, ma'am. What is meant by biosensor? Most of you know, biosensor is a device that measures biological or chemical reactions in a biosample. Simply, I will say, biosensor is converts bioreactive sample to electrical signals. The first biosensor introduced by Professor Leland C. Clark during the period 1918 to 2005. The first biosensor developed detection oxygen level in 1956 with help of electrode. That is called Clark electrode. He is a father of biosensor. Next one. The first commercial biosensor was developed by Yellow Spring Instruments. That is called YSI in the year of 1975 for sensing glucose level in human blood sample. Next one. Developed handheld blood biosensor by iStat in 1992. Next one. The advanced biotechnology, the multiple various domain research involved in biotechnology like optical, electronics, and nanotechnologies. Here displayed different components of biosensor. First one, bioreceptors, transducers, electronics, and display devices. And then analyte. Analyte means unknown biomolecules in biosamples. What is the main role of the bioreceptors? It is pick or specific biomolecules in biosamples. For example, blood is a biosamples. Hemoglobin, glucose, and blood plasma is a unknown analyte. Here displayed different types of bioreceptors like enzyme, cells, abdomer, DNA, and nanoparticles. Biorecognition, that means the interaction between analyte and bioreceptors. At the end of the bioreceptor, it produces one form of signal like light, heat, pH, and mass. But the main role of bioreceptors, it converts biomolecules to biorecognition signals. Based on biorecognition system, we convert to electrical signal with help of different types of transducer. Already know transducer nothing but convert one form of energy to another form of energy. They display different types of transistor, photodiode, thermistor, peakage electrode, and quartz electrode. For example, just consider photodiode. It converts light or optical signal to electrical signals. Various types of photodiodes are the PIN and APT. PIN is nothing but APT is nothing but avalanche photodiodes. PIN already know the maximum sensitivity is produced with the help of avalanche photodiodes. And then the electrical signals move to the display devices via electron signal conditioning or electronic devices. What is the main role of the electronic device? It converts analog to digital signals and also amplified the particular signals, and finally the digital signal displaying display devices. Okay. Here displayed examples of biosensors. First one, pregnancy test. Second one, glucose monitoring, and then SPR based biosensor, and finally infected biosensor from red blood cell. First one, pregnancy test. Here, biosamples recognized in this consider urine biosample. Here, detect HCC hormones. Already know two important hormones are there in women, like estrogen and progesterone. Here, main drawback of this pregnancy tester, this is not reusable. To overcome this drawback, recently my teams introduced optical fiber-based pregnancy tester. The main advantage of this device is it produces high sensitivity and also reusable. Next one, the glucose monitoring devices for diabetic person. It is only monitoring the level of glucose level in the human blood sample. It is an old one. Recently, many handheld glucose monitoring devices available in the market. The third one, Biocore SPR biosensor platform. SPR is nothing but surface plasmon resonance. It is excellent bonding between analyte and bioreceptors. So this produces high sensitivity and also compact devices. Finally, the infected cell biosensor from red blood cell. This is one of the handheld device for identify the infected cell from the red blood cell. This one, based on the different types of transcription, we can classify electrochemical biosensors, thermometric biosensor, piezoelectric biosensor, and optical biosensor. From the optical biosensor, again classified fluorescence, luminescence, transmission, and scattering. Second one, surface plasmon resonance, this is called SPR. Third one, interferometer like Kncet interferometer, Michelson interferometers. Then optical wavegates like directional couplers and single step wavegates. Next one, ring resonator or circulators. Then optical fibers, various types of optical fibers available: single mode fiber, multi-mode fibers, few mode fibers, multi-core fibers, and some facility fibers. Then photonic crystal. Here from 1D or 2D is possible from photonic crystals. These are all the techniques available for biosensing applications. Now enter to the optical fibers because it is high sensitivity and also it is flexibility. That's the reason for to enter the optical fiber. Yeah. Optical fibers. Initially, optical fibers mostly used in telecom application, like transfer the information from one place to another place, like single mode fibers and multi-mode fibers. But advanced technology of optical fibers is also applicable in non-telecom, like sensors, filters, lasik, and other optical components. Let's take some logic gate designing. This is a general structure of the optical fibers. It is made by glass or plastic that carries information from one place to another place. The general optical wavelength range is 100 nanometer to 1 millimeter. This is a general structure of the optical fiber. It is containing three important parts: one for fiber core, cladding, and plastic jacket. The main role of the plastic jacket to support mechanical, to give mechanical strength to the core and the cladding. From the core, here it is filled high index material for effective light confined in the core medium compared with the cladding. Cladding also produces a good strength and also reduce scattering losses. Okay. From the optical fiber, we obtained maximum advantages like higher bandwidth, low transmission loss, compact size, immunity to electromagnetic interference, and high security. Due to numerous advantages of optical fibers, it can applicable various fields like telecommunications, local area networks, cable TV, CCTV, optical fiber sensor, and other optical components. Okay, already discussed the basic structure of the optical fibers. Now, how to effectively confine in the core medium? Okay. Yes, it is possible with the help of total internal reflection mechanisms. The very first point in the total internal reflection mechanisms, N1 must be greater than N2. N1 is nothing but refractive index of the core. N2 is nothing but refractive index of the cladding. This is a total internal reflection mechanism, diagrammatic representations or pictorial representations. Just consider glass or air. The refractive index value of the glass N1 equal to 1.5. The refractive index of the air equal to N2 equal to 1.0. The cladding of refractive index value is very low compared with the core. This is for normal axis. This boundary is considered core and cladding interface boundary conditions. Okay. Now, just pass the light signal at the core and the cladding interface. Here, just consider incident angle theta 1. This is a refracted, refracted angles. Okay. Now, light signal passing from this interface area. Now, the signal is propagated from one medium to another medium. That is called refractions. Okay. Now, slightly increases incident angle from theta 1 the particular angle. Now, the light is maximum propagated at core and cladding interface. That incident angle is called critical angle. Based on the critical angle and incident angle, we can easily classify reflection and refraction. When we incident below the critical angle, maximum amount of light confined from one medium to another medium. Then when incident angle above the critical angle, there maximum amount of light confined in the same medium. That is called reflection. Okay. Here, how to calculate the critical angle? Yes, it is possible with the help of Snell's law. Already know Snell's law. N1 sin theta I equal to N2 sin theta 2. Here, theta I is nothing but incident angle. Theta 2 is a refracted angle. At critical angle, theta 2 is a 90 degree. So sin 90 degrees is considered 1. Okay. Now sin theta c equal to N2 divided by N1. But finally, obtaining the critical angle, theta c equal to sin inverse of N2 divided by N1. This is a basic fundamental mechanism of effective light confined in the core medium. It's any one fibers like single mode fiber, multi-mode fibers, and five-mode fibers, multiple fibers, and specialty fibers also. This one. But how to evaluate light characteristics with the help of some theories? They just noted two important theories: ray theory and for mode theory. From the ray theory, the wavelength of light is much smaller compared to the core size. It just core size is a multi-core fiber. Just you can say multi-mode fibers because here core size is large compared with the input of wavelength. From the ray theory, it is not applicable single mode optical fibers. To overcome this drawback, to move to the mode theory, and also from the ray theory, it cannot evaluate interference, diffraction, and scattering. To only evaluate reflection and refraction. To overcome this drawback, to move to the mode theory. From the mode theory, the core size is very small. It's applicable. For example, just consider single mode fibers. The core size is 10 to 12 micrometer. The mode theory is applicable in single mode fibers. From the mode theory, here the light is propagated in the form of electromagnetic field with the help of Maxwell equation with appropriate boundary conditions. Here displayed, and also from the mode theory we can easily evaluate diffraction, interference, and the scattering light ray characteristics. Here displayed three important modes for transfer electric field TE0, TE1, and TE2 in optical fibers. This consider core, cladding. Core is N1 is something higher index value, N2 is nothing but lower index value. From the lower order mode, like TE0, there maximum amount of light confined in the core medium, that is maximum index intensity or maximum power there in core compared with the cladding. Okay. Next one, TU1 and TU2, very minimum amount of light confined in the core medium. This mode is called higher order modes. TU1 and TU2 is higher order mode, TU2, TU0 is a lower order mode. 0, 1 and out represent 0 and 1 and 2. 0 is nothing but zero crossing in the zero crossing in the core. Here no zero crossing occur like 0. Here 1 zero crossing occur like 1. Here 2 zero crossing occur like 2. Okay. Mostly in optical fibers only consider TE0, this fundamental code, because a maximum amount of power or light confined in the core medium. It is only for applicable in many applications, like not only sensor application, logic gate designs, large mode area fibers, and also lacing applications. Next one, fiber properties and also characteristics. Here displays important optical fiber characteristics. First one, attenuation. Second one, numerical aperture. Third one, pulse dispersion. Fourth one, non-linear effects. Fifth one, endlessly single mode optical fibers. Fifth one, large mode area and birefringence. Okay. From the attenuation, already know what is my attenuation. Attenuation is degraded power level. Here, in optical fiber, the power levels degrade to various phenomena like bending of the optical fibers, scattering, from the bending, micro bending and macro bending, and also absorption. This phenomena support to degrade the power level. This one, numerical aperture. This produce a light ray gathering capacity of the optical fibers, and also it give better bonding between optical source and optical fibers. Next one, pulse dispersion. Dispersion is nothing but broadening of the optical pulse. Just to consider single mode fibers at the initial stage of optic spectral with the optical pulse like just 2 nanoseconds. At the end of the optical fiber, you got 4 nanoseconds. Okay, now pulse is broadening. Due to pulse broadening, we can obtain intersimple interference because maximum more number of pulses propagated in the optical fibers. Due to overlapping of the optical fibers, we obtain intersimple interference and also called crosstalk. To overcome this dispersion, many optical fibers are there, like dispersion compensating fiber and dispersion flattening fibers are available. Pulse dispersion can be classified two types of pulse dispersion: wave gate dispersion and also material dispersions. Okay. Next one, non-linear effects. When maximum amount of power is propagated in the optical fiber, that is non-linear effect is created, like self-phase modulation, cross-phase modulation, SRS and SBS. Sorry, that means Raman scattering and brilliant scattering. Next one, endlessly single mode. That means only one mode is propagated at entire fiber length. That is called endlessly single mode. This large mode area, how effectively light confined in the particular area. That's called large mode area. Endlessly single mode and large mode area properties mostly applicable in lacing application with the bending effect. Okay. Next one, birefringence. It's very important properties for sensing and also filtering applications. Birefringence is nothing but differentiate between TE mode or TM mode or X and Y polarization. When we obtain maximum birefringence, we can easily differentiate both modes like DE or TM or X and Y polarizations. Okay, these are basic fiber properties. Next one, types of optical fibers. Here, single mode step index fiber displayed, grid index fiber, and multi mode step index fiber. First one, single mode step index fiber. Here, only one mode is propagated at entire fiber length. That's called single mode step index fiber. Step index nothing but this is a step index profile. At the core and the cladding interface, we have done sudden change, minimum to maximum. That is called step index. Okay, the core size of the step index fiber 10 micrometer to 12 micrometer. The cladding size is 125 micrometer. Okay, single mode step index fibers mostly applicable in long distance communications. Okay, multi-mode step index optical fibers, the core size is 150 micrometer to 200 micrometer. The cladding size is 380 micrometers. Here, two or greater than modes are propagated in the core medium. The main drawback of the multi-mode step index fiber is only applicable small distance communications. It is not applicable long distance communication and also occur interstable interference and also intradispersion. To overcome the drawback, they move to the graded index optical fibers. From the graded index optical fiber, this is reflecting as per some changes with respect to radial distance. Here, some changes occurred with respect to radial distance. That is called graded index optical fibers. From the graded index optical fiber, we can easily overcome in crosstalk and also crosstalk or intersimple interference and also interval dispersions. The core size of the gradient index optical fiber is 50 to 100 micrometer and the cladding size is 125 micrometers. Recently, many researchers involved in few mode optical fibers and also multi-core optical fibers. What is the mean by few mode optical fiber? Is certain number of modes is propagated in the few mode optical fibers. Recently, Japan is involved in few more optical fiber for spatial digital multiplexing technology. Already know every digital multiplexing, DWM, dense digital multiplexing, or core digital multiplexing. Instead, SDM is nothing but spatial digital multiplexing. Many number of modes confined and propagated to the particular optical fiber. That fiber is called few mode optical fibers. It can support number of a certain number of modes. That's called few mode optical fibers. Nearly above 1 TB data per second per transmission from one place to another place with help of few mode optical fibers. This one, multi-core optical fibers. Here, this are three different types of cores like 3-core, 7-core, and 19 cores. The different structures of the multi-core optical fibers. The main drawback of the multi-core optical fibers, it is create a differential model delay. It's a very important drawback of the multi-core optical fibers, like nothing but DMD, differential model delay. Okay. Multi-core optical fibers are also applicable SDM applications. Next one. Now enter the optical fiber sensors. Optical fiber sensor is nothing but integration of optical fiber communications and also optoelectronic devices. This is a general functional block diagram of the optical fiber sensor. It's considered three important regions or area like an optical source, sensing region or sensing area, and then optical receiver area or detector components. Okay, this is the initial optical spectrum pulse. This is finally get output spectrum. Okay. Here, this is sensing region or sensing devices or sensing fibers. Okay. Now, transmitter or optical spectrum from optical source to sensing region via optical fiber. You just consider single mode fiber or single fiber for effective light transmission from source to sensing devices. Here, this is considered just any one sensing devices with help of optical fibers. Okay. After the end of the optical fibers, I get some output. Through optical detector converted to optical signal to electrical signals. Otherwise, directly I get optical signal via optical spectrum analysis. This is called our disrupted light signal. With help of any one atmosphere effects or internal effects. With the help of disrupted light, we can easily identify the disrupted signals. Like just to consider biosamples. Just to consider biosample, just many components of the biosamples like hemoglobin, glucose, plasma. I just infiltrated biosamples in the core region. Now pass to the light signal in the core region. The light is disturbed. Based on disturbed signal, we can easily identify the particular biosamples. Okay, this is general functional character of the optical fiber sensor. The main advantages of the optical fiber sensor is high design flexibility. It also produces high sensitivity and then compact size, remote sensing, multifunctional sensing, and also label-free detection. Okay, and also it is applicable various field like industrial, medical, military, agriculture. Next one. Based on monitored parameters, we can classify intrinsic sensor and extrinsic sensor. Okay. Now move to photonic crystal fibers. Like it is a special kind of optical fiber. Already know some types of optical fibers already discussed: single mode fibers, multi-mode fibers, few mode fibers, and multi-core fiber. This type of fibers most applicable in telecom field. Okay. This types from photonic crystal fiber, it is a special kind of optical fibers. Otherwise said specialty fiber. It is applicable in commercial field like sensor, filters, and some lasering applications. Okay, this is a 3D view of the photonic crystal fibers. This red color is the buffer jacket or plastic jacket. for producing mechanical strength to the core and the cladding medium. The small dot is represented photonic crystal with filled by air holes. It is supposed to light confined effectively in the core medium. Now I want to create a core. Yeah, just I removed one photonic crystal. That place is like core. This is a core for effective light signal passing at the end of the optical fibers. Okay, here the periodic pattern of microscope parables run along the entire fiber length. This is a refractive index profile of the corresponding photonic crystal fibers. The first photonic crystal fibers developed by Philip Russell and Einstein in 1995. Okay. Why need for photonic crystal fiber from conventional optical fiber? Why not conventional optical fibers applicable in sensing applications or some other application? The main important drawback of the conventional optical fibers is a no design flexibility. Okay, photonic crystal fiber is a high design flexibility. Okay, we can easily modify core cladding or some other materials, but conventional optical fibers is not applicable or modifying any other structural parameters like core and cladding. Like single mode fibers only consider 8 to 10 micrometer core size. Multi-mode fibers is consider 150 to 200 micrometer size. Few mode fibers is consider one parameters, one values. This is not variable. Okay. From conventional optical fibers, the relative index difference between 0.2 to 1%. But from photonic crystal fibers, we have obtained the relative index difference between 0.01 to 10%. Because these big advantages from photonic crystal fiber. We can easily infiltrate biosamples in photonic crystal fibers compared with the conventional optical fibers. Okay. Due to high design flexibility, we can easily attain various optical properties, desired optical properties like enlarged single mode, large mode area, tunable dispersion, high birefringence, and tunable large mode optical nonlinearity and obtain very low loss. Okay. This all the properties obtained with the help of high design flexibility of photonic crystal optical fiber. This is not applicable in conventional optical fibers. Here this plays an important photonic crystal applications. First one, it is also applicable telecom application like dispersion compensation and broadband single mode optical fibers, and also applicable in lasers like it is generated double clad fibers, large mode area fibers, and white light source also applicable in with help of photonic crystal fibers. It is also applicable in metrologic, sensing, logic gates applications, and also medical field, and also finally industrial machining. Okay, now based on light confinement, here differentiate two types of photonic crystal fibers. One for solid core photonic crystal fiber, another one for hollow core photonic crystal fiber. This is a cross-sectional view of the solid core photonic crystal fiber. The small dot is represent microscopic interval. This photonic crystal. Okay, this cap is nothing but distance between two microscopic intervals. It is nothing but diameter of the microscopic intervals. This is a core region for effective light transmission in the core region. Right, okay. Here, light is confined in the core with the help of total internal reflection mechanism, because here refractive index of the core is high compared with the clay. That is called solid core photonic crystal fiber. In solid core photonic crystal fiber, it is applicable in various fields like solitron transmission without affecting any disturbance during the optical pulse transmission in optical fibers. That time need for anomalous dispersion like d greater than 0, like d less than 0, that's called normal dispersion. D greater than 0 something but anomalous dispersion, d less than 0 nothing but normal dispersion. And also easily obtain 0 dispersion wavelength for applicable in super continuum generation high coherence pulses. Okay, and also easily obtain endless single word. That time now v number must be less than 2.405. Next one, all of our photonic crystal fiber. Here, light is confined very low medium compared with cladding with the help of photonic band gap mechanisms. And then from the all of our photonic crystal fiber, only very limited wavelength of or very limited band of signals only allowed in all of our photonic crystal fiber for various applications. It is applicable in high power transmission without optical nonlinear effects. Here, the black is represented by low index it's called cladding. The blue color is represented by core medium. Here, this is a refractive index profile or a light wave propagation cross-sectional view. Here, maximum amount of light confined in the core medium with the help of tight bonding. light bending of photonic crystal fiber. Okay, this is a maximum amount of light confined in the core medium. Here, the core medium's refractive index value is very low compared with cladding. This is a major difference between solid core, hollow core photonic crystal fiber, which is only light confined in the high index medium. Here, light confined in the low index medium. Here, mechanism is total internal reflection mechanism. The hollow core fiber photon mechanism is photonic band gap effect. But from hollow core photonic crystal fibers, only limited particular band, but it's not limited any band. Okay. Here displayed some photonic crystal fiber sensors. From physical optical sensor, we can identify temperature, curvature, or bending levels, displacements, torsions, pressures, refractive index values, particular materials, and electric field and some vibrations. Okay. From the biochemical sensor, we can identify gas, molecular, DNA, proteins, hemoglobins, glucose levels, immunity and pH values, cancers, blood plasma. Okay, so some of the many applications there in biochemical sensors. This visualization for yourself want to display some important applications only. Okay. Okay. How to design optical fibers and photonic crystal fibers? Okay. Here display some display 6 important numerical techniques for evaluating light ray characteristics. First one, finite element method. It is called FIM. It is based on spectrum analysis. Okay, it is fully covered by Thomson mode solver package. Next one, find difference time domain method. It is covered by ASOP and Lumerica. It is fully based on time domain analysis. Next one, beam propagation method, scalar effective index method, plan wave expansion method, multipole method. Okay, for this finite element method is the best one compared with the remaining. Okay, because finite element method we can easily design or analysis complex structure of the optical fibers with low computational time. But finite difference method is applicable, but computational time is high. Okay. Then beam propagation method, scalar effective index method, plan wave and multiple methods are applicable to design a photonic crystal and also various optical waveguides. Okay. Here, just to draw the meshing of photonic crystal fiber. This is a hexagonal shape of the hexagonal periodic arrangement of photonic crystal fiber itself a meshing. Okay, this is for center core region. Here, electric field distribution of the fundamental mode. Fundamental already displayed TE0 or otherwise said LP01, linear polarization mode. It's a very fundamental code. This is only applicable in sensing and some other applications. Okay. Okay, now enter to the out of a photonic crystal fiber for sensing applications. Okay, now I'll start with the cancer cell detection with the help of dual core photonic crystal fiber based refractive index sensor. This paper is published in IEEE Sensor Journal at 2018. Okay, here I proposed dual core photonic crystal fiber structure for identifying the cancer cell detection of various human parts. In this proposed work, just consider 3 important human body: the cervical, breast, and basal parts. Here, what is the main role of the dual core photonic crystal fibers of cancer cell? Is produce high sensitivity and also offer high birefringence with magnitude value of 10 power minus 3. This is my proposed cross-sectional view of the dual core photonic crystal fiber. The corresponding structural parameters are displayed. Okay, the background material is silicon. Here I created dual core photonic crystal fiber. It is a one of the core. This background is silica. This like silica core optical fibers. Another one core is cancer cell cavity. This filling area. This is one of the fiber core. Okay, this size D3 value is 0.6 micrometer. This is for sample filling area. Let's consider blood sample filling area. Okay, next one. What is the main reason for we created big microscopic air walls nearby silica core? This produces a high birefringence. It is the structure of the structure of the core is asymmetric size, not a symmetric, not a circular shape. This is a producer elliptical shape. It is producing high birefringence for easily differentiate X and Y polarizations. Okay. At the microscopic air walls already know the index value of R equal to 1, and then distance between two microscopic air walls, that is called pitch. The value is 2 micrometer, and then the big microscopic air walls diameter of big microscopic air walls dt equal to 2.2 meter. The remaining air walls consider D1 equal to 1.4 micrometer. The remaining air walls support to maximum amount of light confined in the core medium or as cancel cavity mediums. Okay, this is cross section of the proposed dual core photonic for identification of cancer cells. Okay, in the, from the proposed structure, you just consider three important materials: one for silica, another one for aerol, another one for sample. Okay. In numerical analysis, I just consider material selection in terms of refractive index value. Okay, here just I consider first index material is fused silica. Here I derived a refractive index value of fused silica with the help of Selmier equation. This is for Selmier equations for calculating refractive index value with respect to lambda wavelength and temperature. And just consider room temperature 20 degrees Celsius. Okay, next one. Already know the refractive index value of the air equal to 1. Okay, this is basic fundamental one. And then refractive index of the cancerous cell, that is samples. Already know here in the proposed work I just considered three parts of human body from vessel, breast, and cervical cells. Okay, here the refractive index value is slightly deviated at cancerous cell and the normal cell. At the cancerous cell, at 80% obtained 1.38, and normal cell 40 to 60% obtained 1.36. What is the main reason for obtained cancerous cell at 1.38? Here, in the cancerous cell have a maximum protein. That is the reason for a maximum refractive index values obtained in the cancerous cell. Okay. Next one, from the breast cell, the cancerous cell 1.399 and from normal cell obtained 1.385. From the cervical cell obtained cancerous cell 1.392 and the normal cell 1.368. These all these values are calculated with the help of refractometer from this paper I did Sensor Journal 2016. Okay. From this refractive index, now move to the simulations analysis or numerical analysis. Next one, coupling mechanisms, because it's a very important topic for identifying the resonance in particular samples. Okay, here just consider two core or two mode. Already know this is one of the core, this is one of the core. This is the background, which is silica. That is called silica. Light is propagated in the core. That mode is called silica core mode. Here just consider cancer cell cavity is one of the core. Here light is propagated. This is called cancer cell core mode. Okay, two modes are propagated. One mode is silica core mode. Another one mode is cancer cell core mode. Okay. Yeah. Here, electric field distribution of with respect to Z. Z is nothing but propagation distance. For silica core mode equal to I beta 1 E1 plus I K E2. Next one, from cancer cell core mode, there difference between beta 2 and Z equal to I beta 2 E2 plus I K E1. Here, beta 1 is a propagation constant of silica core mode. Beta 2 is nothing but propagation constant cancer cell core mode. K is nothing but coupling strength. E1 is nothing but electric field intensity of the silica core mode or power level of the silica core mode. And then E2 is nothing but electric field intensity or power level of the cancer cell core mode. Okay, K for coupling strength. Here, coupling is nothing but, already know, E2 is nothing but electric field intensity of the cancer cell core mode. It is coupling with the silica core mode with the strength of some values. That's called coupling strength. K. Similarly, for cancer cell core mode, U1, the electric field intensity of silica core mode is coupled with cancer cell core mode with strength of K. Okay. This is for coupling reactions occurring in silica core mode and cancer cell core mode. Okay. This is the electric field distribution of both polarization, X and Y polarizations. Okay. This is for already know left hand side core is cancer cell core mode, right hand side core is silica core mode. This is for cancer cell core mode for X polarization. This is for silica core mode for X polarization. This is for coupling mode for X polarization. Okay. This is for Y polarization cancer cell core mode. This is Y polarization silica core mode. This is for coupling mode for Y polarizations. Okay. Now, how to get the coupling mode? Okay. For identifying the resonance position. Now, already know two modes are propagated in the dual elliptical core fibers. Now, the propagation constant of coupling mode beta plus or minus equal to average beta plus or minus square root of del square plus k square. From the average beta, we can calculate equal to beta 1 plus beta 2 divided by 2 and del equal to beta 1 minus beta 2 divided by 2. Okay. Then based on structure, based on photonic crystal fiber structure, we can classify two types of coupling. One for leakage mode coupling, another for bounded mode coupling. Okay. Just to consider symmetrical size of the dual core. At the time, obtained bounded mode coupling. Unfortunately, the dual core is asymmetrical size. That time occur leakage mode coupling. Here, I generated asymmetrical size of the core. So here produce leakage mode coupling. For leakage mode coupling, the time the beta 1 already know beta 1 nothing but propagation constant of any one core mode, silica core mode or cancer core mode. Period is nothing but propagation constant of cancer cell core mode or silica core mode. Okay. For leakage mode coupling, beta 1 or beta 2 are complex. So they may be also a complex are written by beta 1 is equal to beta 1 r plus I beta 1. This is the real part, the imaginary part. Similarly, beta 2 and they obtained real part and imaginary part. Okay. At phase matching point or coupling point or resonance point. This is for phase matching point or coupling point or resonance point. The time the real parts of beta 1 or beta 2 equal. The del R will be 0. Therefore, the equation 1 can be written as beta plus equal to average beta plus square root of minus del I square plus k square. Okay. So beta minus equal to average beta minus square root of minus del I square plus k square. From this equation, we can classify complete coupling and incomplete coupling. How to classify complete coupling and incomplete coupling based on del I and the coupling strength. When del I less than k, the time the real parts of this is the real parts of beta plus and beta minus have different at resonance position, but imaginary parts are equal at resonance position. Once again, repeat, for complete coupling, when del I less than k, the real parts of beta plus and beta I are different, but the imaginary parts of equal at resonance position and phase matching point. Okay. Otherwise, when del I greater than k, the time the real parts of beta plus and beta I equal, but imaginary part is different at phase matching point. That coupling is called incomplete coupling. Okay, based on del I and greater than, we can classify complete coupling and incomplete coupling. Okay, here I displayed effective index with respect to wavelength flaws, imaginary part or real part. Okay. From this figure I obtained from the console modes of the packages, initially just consider Bessel cancer cell mode. Already know what is the value for Bessel cancer cell cancerous value 1.38. Just so I inserted 1.38 value in the cancer cavities. Okay. The time where is obtained resonance position at Bessel cancer cell core mode. When the Bessel cell cancer cell core mode coupled with the silica core mode, that value, that resonance position is called phase matching conditions or resonance wavelength. Okay, just consider here the white part is effective index, the real part with respect to wavelength. The right hand side is effective index imaginary part with respect to wavelength from 0.86 micrometer to 0.96 micrometer. This is the electric field distribution of the cancer cell core mode for expolarization. This is for expolarization for silica core mode. Okay. At initial point of wavelength at 0.86 micrometer, here obtain the effective index real part value for cancer cell core mode. The value is nearly 1.315. For silica core mode, this is silica core mode. The black line is represented silica core mode. The red color is represented by Bessel cancer cell core mode. The silica core mode, the value is nearly 1.305. Here, at minimum wavelength, the silica core mode value is low compared with Bessel's cancer cell core mode. Now, gradually increases wavelength from lower to higher wavelength. Now, the power or the mode is transfer or coupling from one core to another one core. Here, the light is propagated from this core to this core. Here, the light is propagated from this core to this core. At particular wavelength, the both core have equal power. That time have equal index value or equal real part of index value. That value is called phase matching point or resonance positions for particular cancer cell mode. Here just consider 1.38 cancer cell mode. The 1.38 cancer cell mode resonance position is 0.91 micrometers. The time equal amount of power is propagated at both cores. Okay, at the resonance position, update the imaginary part for effective index not equal. So this is called incomplete coupling. Unfortunately, it is not equal. It is equal. That is called complete coupling. Okay. Once again, repeat. When the imaginary part is not equal and the time real part is coupled, that is called incomplete coupling. When the imaginary part is equal and not real part is not equal, that is called complete coupling. The incomplete coupling and not complete coupling is based on structure. Okay. Here, after coupling, the light is again back to the original position. Yeah, light is again back to at the end of the 0.96 micrometer. Light is again back to the cancel core mode. Here, light again back to come to silica core mode. This is a Bessel cell cancel core mode for effective index real part and imaginary part with respect to wavelength. And otherwise, a dispersal relationship between effective index and wavelength. Okay. Similarly, we can calculate other types of cancer cell modes. Here, just to consider explorizations only. From the effective index imaginary part, we can calculate the loss spectrum with help of this formula. Alpha with respect to x comma y, x is nothing but x polarization, TE mode, and y is nothing but TM mode for y polarizations equal to 8.686 into 2 pi divided by lambda into imaginary part of n effective. Already know what is the value for imaginary part of n effective. This is imaginary part of n effective values into 10 power 6 dB per meter. With the help of this formula, we can easily calculate the loss spectrum. Okay, from the effective index imaginary part. Okay, this consider Bessel cell cancer cell mode and normal Bessel cell mode. Already you know how to identify the resonance positions at particular samples. Okay, here just to consider Bessel cancer cell mode and normal Bessel cell mode. From Bessel cancer cell mode, obtained resonance position nearly 0.1 micrometer. For normal Bessel cell mode, obtained nearly 1 micrometer. But the wavelength shift from normal Bessel cell mode to Bessel cancer cell mode, the value is 90 nanometers. Okay, this is a wavelength shift between two mode. That means normal and Bessel. Okay. Similarly, for obtained Y polarization, here obtained maximum wavelength shift is 120 nanometer compared with X polarization, because here maximum amount of light is propagated into Y polarization mode, because the replicate is maximized values in current Y direction. That is the reason for obtained maximum sensitivity or maximum wavelength shift is Y polarization. That is the reason for obtained maximum wavelength shift 120 nanometer compared with 90 nanometer. And that's another reason for that. The Y polarization mode easily pick up silica core mode. That's the reason for easily obtained maximum wavelength shift 120 nanometers. Okay, this is for electric field distribution of silica core. So silica core mode for Y polarization and coupled mode. So this is for cancer cell core mode. This is silica core mode and coupled mode for Y polarization for Bessel cell detections. Okay, similarly for obtained other human parts samples, cervical cell detection for exploration obtained wavelength shift is 130 nanometers and obtained 170 nanometer for cervical cell detection for Y polarizations. Similarly, the breast cell detection for explorations obtained 80 nanometer. Then breast cell detection for obtained values for Y polarizations values 110 nanometers. Okay, the same phenomena are followed all these cell detections for X and Y polarizations. Okay, based on coupling mechanisms. Okay, now come to peak wavelength with respect to concentration of the cancer cell. From this graph, we have done maximum linearity from the proposed to optical fibers. The various optical characteristics or the optical sensing characteristics available in the optical fibers like sensitivity, resolutions, linearity, and compact size. Okay, here just to draw the 80% of cancer cell to 40 to 60% normal cell corresponding peak wavelength. Here obtained maximum linearity obtained at various concentrations of values. Okay. Okay, now come to the sensing parameters of the proposed dual core photonic fiber for cancer cell detections. Okay, how to calculate the sensitivity and the resolution, because this is very important parameter for is a good sensor or not a sensor, not a good sensor. Okay, here the basic formula for sensitivity S equal to del lambda peak divided by del ns. Here n nanometer nothing divided by RIU. RIU nothing but refractive index unit. RIU nothing but refractive index unit. The formula for del lambda peak divided by del ns. Lambda peak is nothing but resonance peak. Already know what is the peak. This is for resonance peak position. This is for resonance peak position. This is for resonance peak position. The all resonance peak position it plotted with respect to concentration, different concentration values. Okay, from the lambda peak something but peak wavelength for particular cancerous value or normal cell value. NS nothing but the particular refractive index value of set samples like 1.38 to 1.39 already first very first part displayed some values. The values calculated from refractometer. That value is nothing but NS. Okay, this is for sensitivity formula. Another for resolution. Resolution the parameter for resolution or unit of resolution equal to R equal to RIU. RIU or refractive index unit equal to del ns into del lambda minimum divided by del lambda peak. Lambda peak already know peak wavelength. Lambda minimum is nothing but del lambda minimum is nothing but minimum spectral resolution. That value is 0.1 micrometers. See, very important one. This is general value, is a common value for all these sensors. This is del lambda minimum spectral resolution is 0.1 micrometers. Okay, from basic based on the formula sensitivity and resolution, we calculated our vessel cell detection sensitivity, cervical cell sensitivity, and breast cell sensitivity for X and Y polarizations. Here obtained the maximum sensitivity for Y polarizations, like vessel cell like 6,000, cervical cell 7,000, nearly 7,000, and breast cell nearly 8,000, sorry 7,800. Okay. And the resolution, obtain maximum resolution obtained for vessel cell 1.6 10 power minus 5, cervical cell 1.4 10 power minus 5, vessel 1.27 into 10 power minus 5. Okay, this is for not optimized structure sensitivity or resolutions. We now move to the optimized values. Okay, and before enter to the optimized structure of our enhancing sensitivity, what is birefringence? Why you need to calculate the birefringence? Already know what is the difference between what is the main product birefringence? We can easily identify the X and or differentiate the X and the Y polarization. This is a basic formula for birefringence. Beta equal to del n equal to modulus of n x minus ny. N x is nothing but effective index of the X polarizations. N y is nothing but effective index for Y polarization. Here I have plotted different structures or different D2 values. Already know what is the main role of the big microscope parameters to generate maximum birefringence values. Now, now the optimization of D2 like from 1.8 micrometer to 2.24 micrometer with the deviation 2.0 micrometer and 2.2 micrometers. They are obtained maximum birefringence value at 2.4 micrometer at nearly wavelength range is 1.1 micrometer. The value is nearly 3.5 into 10 power minus 3. This is birefringence value for a proposed dual core photonic crystal fibers. Okay. Next one, for enhancing sensitivity, we optimized the big errors. This is the big errors for D2 values from 1.8 micrometer to 2.4 micrometer. In the optimization, just consider only PLR cancer cell mode. PLR is cervical cancer mode is just consider for optimization. Okay. Here just started X polarization and Y polarization. From the X polarization, obtain the maximum sensitivity to 30 nanometer from this loss spectrum with respect to wavelength from 0.6 micrometer to 1.6 micrometer. The what is the here? The D2 value is nearly 1.8 micrometer. This produces a maximum wavelength shift to 30 nanometer. For Y polarization, here obtained at 1.8 micrometer, the value is 300 nanometers. Okay. From this loss spectrum, we can calculate the wavelength shift and sensitivity with respect to diameter of bigger holes. Already know 1.8 to 2.3 I varied. Okay, here obtain the maximum wavelength shift and sensitivity at 1.8 micrometer. Now fix the data equal to 1.8 micrometers. Now move to the diameter of the cancer cell cavity. Yeah, this is a cancer cell cavity. So D3, the value is 0.6 micrometer to 1.3 micrometer. Here obtain the maximum sensitivity D3 you could nearly obtain 10,000 nanometers. Okay. Finally, the optimized structural sensitivity for enhanced sensitivity value is tabulated the wavelength shift for X polarization 90 nanometer. For Y polarization 255 nanometers. The sensitivity value is for X polarization 7916 nanometer per RU. For Y polarization 10,625 nanometer per RU. Also, resolution values for X polarization 1.2361 10 power minus 5. For Y polarization 9.4117 10 power minus 6. This is for my optimized final value for proposed dual core photonic crystal fiber cancer cell detections. Okay, next one. Enhance sensitivity of the hemoglobin sensor using dual core photonic crystal fibers. This was published in Optical Quantum Electronics in 2008. Okay. This structure slightly varied from the dual core photonic crystal fiber for cancer cell detections. It is the main objective of these sensors to investigate the various concentration of hemoglobin level. The value is 5 gram per deciliter to 20 gram per deciliters with the step of 5 gram deciliters in human blood. Okay, here this is produce a proposed dual core photonic crystal fiber cross sectional view. Let's just consider the sample filling area and center airways. Near the center airways, I created dual core symmetrical size. Here I created dual elliptic core symmetrical size. Here I created coupling mechanism in the bounded mode formators. Okay, here the pitch is nothing but equal to 2 micrometer. The air walls D equal to 1.2 micrometer. The cavity size is 1.2 micrometer. These were structural parameters for proposed hemoglobin sensors. Okay. Here, the material selection. We already know the material selection based on numerical analysis and refractive index values. So, for calculating refractive index value of hemoglobin level, NHP with respect to lambda wavelength and also CHP is nothing but hemoglobin concentrations equal to NH2 with respect to lambda, NH is nothing but water refractive index value of the water beta of lambda into concentration of hemoglobin level plus 1. Beta of lambda is nothing but specific refractive increment in deciliter per gram depends upon the wavelength. Okay, CH already know concentration of hemoglobin level in terms of gram per deciliter in human blood. Already know another one refractive index value, another one material for proposed to dual for potential fiber fused to silica. How to calculate this fused to silica with help of Shelmeier equations n square of with respect to lambda and temperatures. Okay. Okay, already know one important thing. So, dual core photonic hemoglobin sensor. Here, designed dual symmetrical core photonic sensor. This is a core, symmetrical core, a sample filling area. Now, just light is confined in any one core. Now, light is propagated at both cores with respect to hemoglobin concentration. The hemoglobin concentration is affected based upon the coupling. Okay. This is for electric field distribution of the proposed hemoglobin sensors. From the bounded mode coupling, four super modes are generated. One for even mode for exploration. This is for even mode for exploration. This is for odd mode for exploration. This is even mode for white polarization. This is odd mode for white polarization. What does it mean by even mode and odd mode? Even mode is nothing but the light is propagated in same directions. That is called even mode. The light is propagated at dual core at different opposite directions. Same direction, that is called even mode. So opposite direction nothing but odd mode. Okay. This is called even mode for X and Y polarizations or mode for X and Y polarization for bounded mode coupling. This is not a leakage mode coupling, this is bounded mode coupling because a generated dual core in symmetrical form. Okay. Now, from the bounded mode coupling, how to evaluate or how to calculate resonance positions. Okay. Yeah. This is basic coupling characteristics of the symmetrical core or bounded mode coupling. The basic formula for LC is equal to lambda divided by 2 modulus of Ne1 minus N0. I is nothing but X and or Y polarization. Ne1 minus N0 is nothing but index difference del Ne0. LC is the coupling length. LC is nothing but coupling length. Based on coupling length, we can easily identify or calculate fiber length. Based on coupling length, we can identify or calculate coupling length. Mostly the fiber length, maximum of coupling length. This is a default one. Okay. Here, this is plotted index difference with respect to wavelength from 700 nanometer to 900 nanometer with various hemoglobin concentrations for 5, 10, 15, 20 gram deciliters. Similarly, this is for X polarization, this is for Y polarization index difference with respect to wavelength. Okay, this is for this is for index difference between X and Y polarization plotting. These values are obtained from COMSOL multiple software also. Okay. Next one, from the index difference, we can calculate coupling length. This is for plotting for coupling length with respect to wavelength. Coupling length and the index difference must inversely proportional. Okay, these values are minimum to obtain the maximum values at minimum wavelength range. Okay, the maximum coupling length at 700 nanometer nearly 5 gram deciliter obtained 4.5 millimeters. Okay, for X polarization, for Y polarization nearly 3.9 millimeter for Y polarization at 5 gram per deciliters. Okay, from the coupling length and index difference, move to the transmission spectrums. Okay, move to this transmission spectrum. From this transmission spectrum, basic formula for transmission spectrum, TR equal to 10 log of output power divided by input power. Okay, this is the basic formula for output power with respect to lambda equal to sine square of n even minus n odd even mode odd mode with respect to X or Y polarizations by L divided by lambda. Here L is nothing but fiber length. The fiber length is uh, fiber length is must be there in maximum of coupling length or this can be 10 times maximum of coupling length. So this is short formula for output power sine square of 10 Ne naught by L divided by lambda. Okay, this is transmission spectrum for different hemoglobin concentration. From this transmission spectrum, we easily identify resonance position with various concentration of hemoglobin level. For example, for exploration, we obtained at 5 gram per deciliter, the value is nearly 875 nanometers. For 10 gram per deciliter, obtained nearly 825 nanometers or 830 nanometers. And near at 15 gram per deciliter, obtained nearly 800 nanometer. For 20 gram deciliter obtained 750 nanometers. Similarly for Y polarization, here when we increase the hemoglobin level from 5 gram per deciliter to 20 gram deciliter, the resonance position go to the lower side from higher wavelength to lower wavelength. That is called blue shifted. When your resonance position move to the higher wavelength, that is called red shifted. Once again repeat, when your resonance position move to the lower side, that is called blue shifted. When your resonance position move to the higher side, that is called red shifted. Okay, yeah, here displayed peak wavelength with respect to hemoglobin concentration from 5 gram per deciliter to 20 gram deciliter. From this graph, we update high linearity. Okay, based on least mean square method, we can calculate this formula, linear fitting equations. For X polarization, minus 7.992 into hemoglobin concentration plus 912.25. For Y polarization, minus 7.66 into hemoglobin concentration plus 903.35 values. From this linear fitting equation, we can easily identify R square value. For X polarizations, obtained R square value is 0.996. For Y polarization, obtained R square value is 0.99598. Okay. Here, the R square values come to nearly equal to 1. This is best one good linearity sensors. This is a maximum sensitivity also. Okay. Now, this sensitivity plot for different optimizations hemoglobin structures. Like first figure, just consider sensitivity value and also equally measure length, fiber length also. With respect to 1.0 THP value to 1.6 THP values in the micrometers. Here obtained maximum sensitivity at nearly at 1.6 micrometer. The value is 8 to 10. Sorry, the value is nearly about 9. About 9 sorry, this value is nearly about 9 nanometer per gram deciliters. At the time, obtained the length is 8 10 to 12 centimeters. It's the main drawback of this one, the optimized values. So now consider optimized values at 1.2 micrometer, the optimal values if 1.2 micrometer, they get just consider the sensitivity value is nearly 8 nanometer per gram per deciliter, and also obtain the length is equal to nearly 3.7 or 3.2 centimeters. Okay, this is for length of fibers. Similarly, for again optimized ROL diameter from 1.2 micrometer to 1.8 micrometer. Here also, I feel same feeling previous one. Like here obtained maximum sensitivity about 9 gram per but the time the length is high, like nearly 6 to 7 centimeter. Now go to the optimized value at 1.2 micrometer. But finally, optimized sensitivity with compact length. For exploration 8.01 nanometer per gram per deciliter, that length is 3.7 centimeters. For Y polarizations, value is 7.68 nanometer per gram per deciliter. The value is 3.2 centimeter for Y polarization. This is for optimized hemoglobin sensors sensitivities and the length values. Okay. Next one, how to calculate glucose sensors with the help of tricore photonic crystal optical fibers. Okay, in the previous first one, cancer center dual core photonic crystal fiber, the asymmetrical structure. In second one, hemoglobin sensor for symmetrical structure. In third one, tricore photonic crystal fiber for blood glucose sensor. This one is published in IIT Optoelectronics 2018. Okay. Here, what the main objective of this tricore photonic crystal fiber to detecting various glucose concentration of human blood sample is considered 10% to 40% level. This type of 10%. Here, this tricore. I created tricore. This is one of the silica core. This is one of the silica core. I just consider center cavity values GT equal to this blood sample filling value DT equal to 0.9 micrometer. D1 microscopic arrows the 1.4 micrometer. The big microscopic arrows D equal to 2.2 micrometer for creating high reference level. The background material is silica, and then remaining arrows index value are equal to 1. Okay. What is the main reason for to create tricore? For instance, choosing from X polarization to Y polarization. This is for demuxing or muxing. The main advantages of the tricore photonic fiber compared with dual core photonic fibers. Here the effort index values calculate the effort index values of the glucose solutions with different concentration n equal to 0.2015 into C plus 1.3292. See nothing but concentration of the glucose level in terms of percentage. And we already know the effort index value of the glucose solutions in blood samples. Okay. Here, the same coupling mechanisms also here also followed tricore photonic crystal fibers. This is for a more propagation of silica core or liquid mode. Liquid mode is nothing but this is for the cavity core mode is nothing but liquid core mode. Okay. The silica core mode for X polarization, silica core mode for Y polarization. What is the main reason for equally power distributed at both core? Because the same symmetrical structure is silica core. There is a reason for equally power distributed at both cores. Okay. This is liquid core mode for Y X polarization. This liquid core mode for Y polarization. This coupling mechanisms are obtained from Thomson mode solver packages. Okay. This is coupling reaction for tricore photonic crystal fiber. This is deviated from dual core photonic crystal fiber. This is for X polarization. This is for Y polarization. At the minimum wavelength, maximum light confined only in the silica core mode for symmetrical structures. Not maximum light confined in the liquid core mode. Slightly wavelength is increases. Little amount of power is transferred from silica core mode to liquid core mode. At particular resonance positions, maximum amount of equal amount of light distributed at silica core mode and liquid core mode. Okay, this is for right core mode coupling mechanism or reactions in X polarization, and this is for similar for Y polarizations. Okay, this is for dispersion relations with respect to effective index and also wavelength. Okay. Yeah, just to consider glucose concentration of 30% to the values. The value is nearly 1.392 index values. Like yeah, there are then maximum coupling reaction occurred 0.95 micrometer for X polarization. For Y polarization, nearly obtained 0.825 micrometers. Okay, this is for real part of effective index values. This is imaginary part of effective index values in silica core mode values only. Okay. This one, from the effective index of imaginary part, we can calculate a loss spectrum or confinement loss With respect to dB per meter, the basic formula for loss spectrum already know. With respect to wavelength for X polarization, Y polarization, we obtained maximum resonance position obtained nearly 10,000, 10 percentage, at value nearly 1.25 micrometer, 20 percentage, 1.1 micrometer, 30 percentage, nearly 0.95 micrometer, at 40 percentage, at zero point 0.8 micrometers. Okay. Here also the resonance position shifted from lower wavelength to higher wavelength. Sorry, higher wavelength to lower wavelength. That is called blue shifter. Similarly for Y pulses also follow same coupling mechanisms also. Yeah, displayed or plotted peak with respect to glucose concentrations. It's about maximum linearity, produce high sensitivity. The values 384 6.153 nm per RU for X, for Y polarization 5334.980 nm per RU. In terms of percentage sensitivity value for X polarization 10.661 nanometer per percentage, for Y polarization 14.333 nanometer per percentage. Okay. Okay, now move to the structural optimization for enhancing glucose sensitivity values. Initially, just consider glucose cavity. This was glucose cavity D2 values from zero point 0.6 micrometer to 1.3 micrometer. At optimization level, just consider two concentration value like 10% and 20%. From this figure, we obtain the maximum wavelength shift at zero point 0.9 micrometer, the value is 140 nanometers. Next one, from this figure, this is plotted confinement loss spectrum from 1 micrometer to 1.3 micrometers. Here, band maximum wavelength shift at 1.3 micrometer, the value is 190 nanometer. From the wavelength shift, we can easily identify the sensitivities. Okay. Okay, this is a plot for wavelength shift and sensitivity. The maximum sensitivity obtained nearly about 10,000 nanometer per RIU, and nearly obtained wavelength shift to 220 nanometer for X polarizations. Okay, next one. Now fixed D equal to 1.9 micrometer. Next one, the pitch variations from 1.9 micrometer to 2.3 micrometers. We obtained sensitivity at maximum 22,000 at 1.9 micrometer pitch variations. Okay, now, it's most of all the structural variation obtained with help of compact length of value is 1 millimeters. Okay, it's a big advantage of the tricore photonic crystal optical fibers. This tabulator optimized structural sensitivity and wavelength shift and the resolution. The value for X polarization 470, for Y polarization 430. For X polarization sensitivity 23,000, nearly 23,000 values nanometer per RIU. For Y polarization 21,782.17 nanometer per RIU. Resolution X polarization 4.287 in 10 power minus 6 RIU. For Y polarization 4.686 in 10 power minus 6 RIU. Okay. This is for optimized final sensitivity and wavelength shift resolution values for proposed tricore glucose sensors. Okay. Next one, last three sensors are discussed solid core photonic crystal fibers like cancer sensors, hemoglobin, and also glucose sensor. It's most maximum light confined in the eye index medium. Already know at beginning initial stage before come to the applications, different types of photonic crystal fibers. One for hollow core photonic crystal fiber, another one for solid core photonic crystal fibers. Solid core photonic crystal fibers have a maximum amount of light confined in the core medium combined with the cladding with of total and reflection mechanism. From the hollow core microscopical fiber, there maximum amount of light confined in the low index medium with help of photonic band gap mechanism and also only applicable particular band wavelength. Yeah. This work is published in item Texas known as Biosensors 2022. What is the main objective of this hollow core microscopical fiber? To detect the plasma cells in blood serum. In this fiber, I fabricated and also analyzed the structural sensing characteristics. Okay, this may propose to all of our microstructure optical fiber plasma sensors. This is my structural parameters values. The center part of core size is D equal to 122 micrometers. This is soft glass. Here just consider different meters of the analyte. First just consider empty core. That means air value n equal to 1, and just consider filling area n equal to water value is 1.333 and also plasma cell in different blood serums in different concentrations. This is a numerical analysis electric field distribution of the all core microstructure optical fiber plasma cells. This analysis is fully complete based on COMSOL solar packages. Okay. Yeah. These fibers are fabricated with help of nanostructure glass technology from Russia. This is a fabricated all-over microscopical fibers. This is a light confinement areas. Like we are already know, you just consider plasma cell detections in blood serums. Okay, out to different cell blood serums. Okay, just to consider whole blood after centrifugation, 45% of total blood come to the bottom sides, clotted blood. Okay, just less than 1% of blood is moved to platelets. Okay, and then 55% of total blood is then blood serum. From the blood serum, this blood serum, yellow color blood serum, this is clotted blood, this is platelets. From the 50% of total blood serum, we can easily calculate that plasma cells from the blood serum. So, and we just consider blood serum with some diluted water. Ratio of the plasma dilution with water 1 over 8, 1 over 4, 1 over 2. We just get the three concentrations values 1 over 8, 1 over 4, 1 over 2 are the corresponding refractive index values of plotted. This refractive index values is evaluated with the help of refractometers. Okay. Okay. This is the experimental setup of proposed holochromic microscope optical fibers. Okay. Here, just consider three parts of one source, another for sensing mediums, another for data spectrum analysis. Okay, this is smart cover. It is holding a holochromic microscope optical fibers with length of 6.1 centimeters values. Okay, this is for a smart cover for holding the holochromic microscope optical fibers. This is for holochromic optical fibers length of 6.1 centimeters. Okay, what is the main node of this lens to collimating to adjust the light signal to the core medium of the holochromic microscope optical fibers. Here, the proposed holochromic microscope fiber with the length is 6.1 centimeter. Yes, here we used to soft optical glass. Already know here we used to soft optical glasses. It is composed to 72% of silica and 16% of sodium oxide, and there's some smaller amount of some small percentage values of gallium oxide and magnesium oxide and barium oxide. So that refractive index of the soft glasses can equal to 1.519. Okay. Now just pass the lamp signals or light signals through the hollow core optical fibers. At the end of the optical fibers, obtain some optical spectrum with the help of spectrum analysis. From the spectrum analysis, we obtain some minimum power spectrum or loss spectrum. Based on the optical spectrum signals or power spectrum signals, we can easily identify the infilling area of the blood serum concentrations values. Okay. Yeah. Yeah. Just to consider blood serums, water diluted with the blood serums, and empty waters and empty cores. But initially, just to consider empty core, just observe what is the transfer spectrum for empty core. Already know here, just already said, hollow core microstructure optical fibers only allowed a particular band. Yeah, it just only allowed 400 nanometer to 900 nanometers values. Okay, this is a power spectrum for measured and simulated values for a measured with help of raster technologies and it's a simulation with help of COMSOL most of the packages. Okay, mostly approximately completely equal with except the intensity values. Okay, this is a experimental and simulated blood serum loss spectrum, sorry, power spectrums. Okay, I just consider water and also different ratio of blood serum with diluted water. 1 over 4, 1 over 8, and 1 over 2. Okay, here this is the transverse spectrum. Here obtained over resonance peak, here also obtained over resonance peak, maximum intensity values. So, just consider a maximum intensity values like this area from nearly 626 nanometer of water obtained 626 nanometer at over 1 over 4 blood serums value obtained 645.6 nanometers, and then serum 1 over 8 obtained 641.55 nanometer resonance positions, and finally serum forward to obtain 657 nanometer. Okay, this is for experimental analysis, spectrum analysis. From the COMSOL modular packages, they obtain the loss power and core. As in similar called extensive spectrum also, no problems. There are similar like similar values from the experimental analysis, like from 611 nanometer for water, 632 nanometer for serum 1 over 8, 639 nanometer for over 1 serum 1 over 4 and 650 nanometer serum 1 over 2. Okay. From the experimental analysis and the stimulus analysis, calculated sensitivity values for simulated equal to 5636.3 nanometer per RIU for measured 7454.5 nanometer per RIU. This is my proposed experimental analysis and also compare the simulation also values also. Okay, next one, reconfigurable surface plasmon resonance based refractive index sensor for biomedical applications. Here, one new important materials are incorporated in the proposed optical fibers. That means phase change material. What is the main reason for we incorporated the phase change material for? It's reconfigurability. It's a reconfigurability. And before enter to the proposed to work, first of all, what is meant by surface plasmon resonance? How to generate the surface plasmons? You should consider metal and dielectric mediums like this format. Okay, epsilon D is nothing but dielectric permittivity, epsilon M is nothing but dielectric metal. Sorry, permittivity metal. Okay, just to incident or light signal at the interface between dielectric and metal. Here observe one small vibrations or some amount of collective electric oscillations propagated at the interfaces. Okay, that is called surface plasmons. The excitation of surface plasmon by light is called surface plasmon resonances. This surface plasmon resonance mostly depends upon the metal thickness, refractive index value of the dielectric materials, or refractive index value of the metals, or incident wavelength, or incident angle. Okay, this one. The main features of the surface plasmon resonance is excellent bonding between analytes and gold or metal values, okay, or dielectric values. Okay, it is only maximum applicable in shorter wavelength as compared to excitation realite. Okay, this was applicable in eminence wave enhancement. With the help of eminence wave enhancement for obtaining maximum sensitivity with the complex size. Is already said is used for interfacing bond. Okay, surface with analytes. Okay, let's say propagation along the surface. With the help of propagation along surfaces, we can easily interact with the target molecules. Yeah, just I flattered, just proposed one class prism-based SBR biosensors. This is for targeted biomolecules. This immobilized receptor bioreceptors values molecules. This is for metal. That's a gold. Yeah, it's metal. Okay, here like this is a dielectric materials. Now just incident light signal from the light source to this area. And small vibrations of surface plasma resonance generator. Here, the surface plasmon signals is coupled with the targeted biomolecules. The resonance positions occurred based on surface resonance positions, surface plasma signals, and targeted signals coupling mechanisms. Based on this coupling mechanisms, the resonance positions varied, or based on refractive index values target molecules, the resonance values varied. Okay. Next one, and already said the phase changing material for reconfigurability. Okay, this is new work for in photonic crystal fiber for reconfigurability. What is the main for reconfigurating? Switching. That's all switching. Okay. What is the main advantage or objective of the phase change material? It's the excellent switching properties. We used to consider two phases there in phase change material. One for amorphous phase, another one for crystalline phase. Like when the phase is changing, with the help of optical signals or external activations like optical signals, electrical signals, and thermal activations. Okay, when you applied at 180, 160 degrees Celsius, the time the phase is changing from amorphous phase to crystalline phase. First of all, the structure of the amorphous phase is like this format. The molecules arrangement is not irregular, sorry, regular shape. So like regular shape. Okay. In crystalline phase, like regular arrangement of molecules in regular shape. Now convert amorphous phase to crystalline phase. Okay, that time applied 160 degrees Celsius. Okay, but one beauty of the phase change material is again back to come to amorphous phase at 600 degrees Celsius. That's called recycling capacity. Also have phase change materials. That's called reconfigurability. Okay, the main phase change materials are available. Okay, one GST, GSST, and GST. Mostly in GST one mostly used in photonic crystal fibers because it has excellent switching property compared with GCT and GSST. The compound materials of GST germanium, antimony, and tellurium. Okay, this display the advantages of the phase change materials like high stability, low optical loss, high crystallization rate, and good reversibility. That is the reason for come back to the crystalline to amorphous phase. Right, it's a good reversibility. Okay. Here, this is experimentally evaluated refractive index value of the GST materials with help of NTU Singapore. Okay, because in this fabricated phase it's not available. The reason for these values fabricated or experimentally evaluated from NTU. Okay, they are displayed refractive index values in the real part is a complex form with respect to wavelength from 0.5 micrometer to 3.0 micrometer. From this figure, the index difference between both phase, like crystalline phase and amorphous phase, from 0.5 micrometer to 3.0 micrometer. But the main beauty of this from this flower above nearly 1.25 micrometer maximum index difference from amorphous phase to crystalline phase. Yeah, like this format. Maximum index difference obtained above 1.25 micrometer. Okay. Because that time what is excellent switching from one phase to another phase. Okay, that is the reason for I put del n values nearly like 2.5. Okay, similarly del k values like nearly above 1.5, 1.7 like values. Okay, already know the phase change model of GST is a reversibility switching with sub nanosecond scale times. It is also applicable in mechanical tuned optical devices and also light modulators, polarizing reflectors, and also optical limiters. Okay. First time my team introduced phase change material in photonic crystal fibers. It is a producer excellent sensitivity. Yeah. Here I propose to D-shaped photonic crystal fiber reconfigurable refractive index sensors. The D-shaped photonic crystal already in previous one mostly full fibers, full photonic crystal fibers only displaced. Here they to consider side polished photonic crystal fiber that is called D-shaped photonic crystal fiber. Otherwise, once again repeat, side polished photonic crystal fiber. Otherwise, D-shaped photonic crystal fibers. Yeah. This is for small air walls as a photonic crystal for effective light confinement in the core medium. This is a core medium for silica core medium. It's a D3 big air walls for producing a high birefractive values 2.4 micrometers and then pitch equal to 2 micrometer. This is the distance between two microscopic air walls. The top of the side polished or D-shaped photonic crystal fiber. This is considered three important blocks. One for GST material, another one for gold, and then sensing medium or sensing area. Yeah. The thickness of the phase change material GST 14 nanometer. This is optimized values. Yeah. This one. The thickness of the gold layer is 12 nanometer. It is also on the optimized values. Okay. In this proposed work, the configurable reflector sensor I just consider index value 1.3825 to 1.395. The step of 0.025. Okay, this is a cross section view of the proposed D-shaped photonic crystal fiber. From the photonic crystal fiber, here use of gold materials. Yeah. The refractive index or permittivity of the gold materials are calculated with the help of Drude model. Epsilon equal to 1 minus omega p square divided by omega square plus I omega 2p. Here, omega p is nothing but plasma frequency, and dou p is nothing but damping rate. And also omega p value is equal to 9.062 electric volt and dou p equal to 0.070 electric volt. Here, how to coupling mechanisms are created for identifying the resonance positions. This is a sensing medium, or you just consider any one analytic values like 1.3825 to 1.395. Okay. Here, small small oscillations or small amount of small vibration generated with help of engagement values, like eminence values. This surface plasmons is coupled with silica core board that where resonance position is called phase matching point. Okay, I will explain later this area. Yeah, this person relationship between effective index and with respect to wavelength, and also what is the loss spectrum for amorphous phase and crystalline phase. Here just consider two phase of analysis. One for amorphous phase like AGST, another one for crystalline phase GCGST. Okay. In this spectrum analysis, just consider index values 1.3825. Okay. Here for amorphous phase GST materials, this was silica core mode, this was surface plasmon mode. Here, silica core mode and surface plasmon mode is coupled at resonance position value is 1.30 micrometers. Okay, the index value is 1.385. Based on different index values, the resonance position is varied, like based on index value, different index values of analytes. Okay, here amorphous phase of GST materials, the refractive index, effective index of the real part is not equal. The last part, the imaginary part is come to equal. That is called complete coupling. From crystalline phase of GST materials, the real part is come to equal. The imaginary part is not equal. The main reason for this both mechanisms are complete coupling or incomplete coupling, like GSTs. For amorphous phase, the general phenomena for amorphous phase, it is a low absorption. It is the main reason for here obtaining minimum loss spectrum values. Okay, here crystalline phase have a high absorption, so here also obtain nearly 450 nanometer dB per centimeters at resonance position. That is the reason for complete coupling and incomplete couplings. Okay. Okay, here displayed some loss spectrums for different analytes like 1.3825 to 1.395. From the 1.385, the main role and advantage of the phase change materials here just consider amorphous phase and crystalline phase. The blue color surface is amorphous phase, the red color surface is crystalline phase. The switching between amorphous phase and crystalline phase at 1.382 analyte value is 0.1 micrometer 100 nanometers. Similarly, for at 1.3825 at 0.14 micrometers, and then at 1.3875 advent 0.22 micrometer, the 1.395 advent 0.34 micrometers, and then 1.395 advent 0.46 micrometer, and 1.395 advent 0.58 micrometers respect to wavelength. What is the main beauty of these loss spectrums? They are made maximum switching at 1.395 micrometers. It also produces high sensitivity. Okay, this is excellent switching property at 500 nanometers. Okay, here produced peak wavelength with respect to analyzed values. From this peak wavelength plot, calculated linear fitting equation with help of least mean square method. This is a basic equations for linear fitting equations. From this equation, we can calculate our square values like 0.943061 for amorphous phase, 0.972953 for crystalline phase. It comes to mostly come to nearly equal to 1. So it's a good linearity compared with amorphous phase. And also crystalline phase produces high sensitivity compared with amorphous phase. Okay. Yeah. Here displayed wavelength shift and the sensitivity. Here are the maximum wavelength shift occurred at crystalline phase like nearly 650, so nearly 640 nanometers. Yeah, like this one, like this area, nearly 640 nanometers at 1.395 analytes values. Okay, for amorphous phase, nearly 160 nanometers are then wavelength shift. From the wavelength shift, we can calculate sensitivity with help of RIU values. For amorphous phase, 12,800 nanometer per RIU. For crystalline phase, 51,200 nanometer RIU. Okay, then obtain resolution values. Amorphous phase 7.8218125 10 power minus 6. For crystalline phase 1.9531 10 power minus 6. What are the main advantages of these? Reconfigurable D-shaped photonic crystal fibers of compact plane and also produce high sensitivity, and also it is producing excellent switching property from amorphous phase to crystalline phase. What are the applications of reconfigurability? It can easily divide smaller size of the biomolecules and also higher size of the biomolecules. For example, for easily identify smaller size of biomolecules, consider amorphous phase of GST. And now move to the higher size of biomolecules, consider at crystalline phase, like the value is 51,000 nanometer per RU because it is excellent switching properties from amorphous phase to crystalline phase. Yeah, yeah. It is compared, proposed to SPR-based photonic crystal fiber for reconfigured applications with the existing one. It produces excellent output, sorry, excellent sensitivity and also reflecting the values compared with the existing one. Like internal metal coated SPCF sensor produces 11,000, single layer coated PCF produces 15,000 nanometer, scaled down photonic fiber SPR based nearly 30,000, and nearly titanium oxide and gold based DC photonic crystal fibers produce 46,000 nanometer per RU. And it's a photonic quasi crystal fiber based SPR produces 70,000 nanometers. And these shaped only SPR, not using any phase material, that's produced 31,000 nanometer. With help of phase change material, we obtained 51,200 nanometer per RU. Okay. Okay, this is the next one. So detection of blood glucose with hemoglobin content using combat photonic acid fiber. Here, simultaneously to identify the glucose and hemoglobin level with help of dual elliptical core photonic crystal fiber with compact size. Yeah, it is a produced. This work is published in IEEE Transaction Bioscience in 2020. Okay. This may propose a cross-sectional view of the dual elliptical core photonic crystal fibers. Yeah, this is structural parameters of dual elliptical photonic crystal. The pitch size is 3 micrometer, arrow size is 2.8 micrometers, and then the size of the minor axis, major axis of the dual elliptical core R1y and R2y equal to 1.2 micrometer, and R1x, R2x equal to 1.215 micrometer. This is major axis, this is minor axis. Okay, background material silica. So the remaining arrows, and here is infiltrated blood samples for identification of hemoglobin and glucose values. And this is a 3D view of the dual elliptical core photonic crystal fibers. This is electrical distribution of the dual elliptical photonic crystal fibers. Here, generated two structure of the elliptical cores, one for asymmetrical structure, another for symmetrical structure. Okay, here just analyze asymmetrical or symmetrical also. Here, electric field distribution of the dual elliptical photonic crystal fiber for symmetrical structure because maximum amount of light contained equally on both cores. Okay. Okay. How to investigate the blood glucose level with influence of hemoglobin level? This is a basic fundamental formula for calculating the refractive index value with respect to glucose solutions and also hemoglobin solution with help of wavelength. Okay, this for glucose refractive index value with respect to wavelength equal to NPHP with respect to lambda plus 0.1515 into glucose concentrations. Yeah, yeah, NPHP is nothing but photons, hemoglobin's concentration values. NP of lambda plus alpha into hemoglobin concentration. Here NP of lambda equal to photons concentration with photon refractive index values with respect to wavelength at 1.385 for this formula. Yeah. Based on this formula, we can identify NP of with respect to wavelength. Okay. This is a plotted effective index with respect to wavelength from 1.20 micrometer to 1.6 micrometers with respect to 120 gram per deciliter hemoglobin concentration is various hemoglobin glucose values, like consider 10 gram per deciliter to 100 gram deciliter with respect to 20 gram per deciliter values. And also let's consider hemoglobin values 140 gram deciliter similarly for different glucose concentration, or consider 160 gram per deciliter for hemoglobin and also very different glucose values from 0 to 100 gram per deciliters. Okay. This is the glucose level with influence of hemoglobins. Simultaneous identification of glucose level of the hemoglobin values also. Okay, this is my analysis of symmetrical electrical score, asymmetrical electrical score, power spectrum. Okay, From the symmetrical elliptical core, they are obtained minimum shift from 0 gram per deciliter to 100 gram per deciliters. Okay, the wavelength, the length is L equal to 1.8 meter for X polarization and also Y polarization. The dotted line is represented by Y polarization, the solid line represented by X polarization also. Okay, for asymmetric elliptical core, we obtained maximum shift from 0 gram per deciliter to 100 gram per deciliters. Okay. Here also they produce a maximum sensitivity because here also produce due to maximum wavelength and also the length of dual elliptical photonic crystal fibers is very minimum like L equal to 0.276 millimeters. For Y plus also L equal to 2.239 millimeter. So approximately completely equal both X and Y polarizations. So what is the conclusion for dual elliptical photonic crystal fiber? Here generate maximum sensitivity with compensates in the form of asymmetrical dual elliptical core photonic crystal fiber. What is the reason for asymmetrical dual elliptical photonic crystal produce high sensitivity? Because here the coupling length is come to very minimum. So we can easily light transfer from one core to another core. Yeah, this area. This is dual elliptical core. Where for minimum coupling length, we can easily power or more transmission from one core to another core. That is the reason for asymmetrical multi-core generate high sensitivity with compact size. The value is 0.27 millimeter range. Okay. Now to the final applications of photonic crystal fiber-based bending sensors. Here, fiber-based bending sensors for human body joints. Okay. With the for bending optical fibers. There are different types of human body joints and movements are there in human, like knee, ankle, shoulder, elbow. This all the joint movement we can easily identify with the help of optical fibers. Okay. In these applications, initially only used plastic optical fibers and also multimode optical fibers. From these plastic optical fibers, it is applicable to monitoring the lumbar spine movement. This is a structural fascination of the plastic optical. This is plastic optical fibers for monitoring lumbar spine movement. Based on movement, we can easily identify the position of the movement. Okay. What is the main drawback of the plastic optical fiber? It is not flexible, easily damaged. To overcome the drawback, move to the multimode optical fibers. So monitoring the lower back bending. Okay. Here, four kinds of fibers here used. One for transmitting fibers, one fiber is used in transmitter side, three fibers used in receiver side, like this receiver side, this is transmission fiber. Based on movement or based on direction, the intensity is various. Now we obtained the various intensity on three kinds of optical fibers. For angular tilt in lateral direction axis, a maximum amount of power confined only this area. Here less very minimum amount of power confined this both course. Okay. Similarly for angular tilt in sagittal direction for y axis, similarly for example y axis, for x axis, for y axis maximum amount of light confined in the upper receiving fiber area, minimum amount of light confined in the lower receiving area. Based on the power or based on the transfer spectrum, we can easily identify the direction of the angular tilt or x or y position values. Okay. What is the main? Here also some drawback of the multiple optical fiber is produce a very low sensitivity. Plastic optical fibers also produce a low sensitivity, but it's a very damageable. But multimode optical fibers produce a low sensitivity. Okay. To overcome this drawback, move to the photonic crystal fiber based bending sensor. Here displayed single core photonic crystal optical fibers. Under series displayed dual core photonic crystal optical fiber for bending sensors biomedical application. Bending sensor with help of photonic crystal fiber not only applicable biomedical applications and also apply structural health monitoring in civil construction sorts also to easily identify the bridge damaging level. Okay, you just consider this is a transmission point. This is for reflection spectrum analysis. This is for proposed or fabricated single core photonic crystal fibers. These photonic crystal fibers, one part is a fixed, another part is transition edge, the movable area. Here, The photonic cell fibers is fixed center part with alpha single mode fiber, one area single mode fiber, another one is connected single mode fiber for light transmission in photonic cell fibers. Based on the bending or based on the transverse spectrum, we can easily identify the bending areas or bending angle or bending range or bending is mostly done in centimeter level or millimeter levels also. Okay. Here, based on coupling reactions, here based on coupling reaction, we can easily identify the bending range values. It is also similar like previous ones, like single mode fibers connected to one end, another one is connected to the another one single mode fiber. One single mode fiber is connected to the one core of the one core. Single another one single mode fiber connected to the second one core. Okay, based on bending, yeah, like this is based on bending, the light is tilted. The power levels vary. The variation of power level we can easily identify the bending level values. Okay, here the transient spectrum applied coupling mechanisms. Here, the transmission spectrums update with alpha interferometer techniques. This is my final one. Thank you. This is my references. Any queries, any doubts, feel free to ask it to me through email ID and mobile number also.
Participants, any queries you can ask now.
Okay, no problem. If any questions or if any problems, if you have any problems, please send to me through email and mobile number also.
Yes, I think there is no more queries from participants itself.
Okay.
Let me wind up the session, sir.
One second, if anyone accident. Any
Sir, there is one
specific?
question. Yes,
Yeah.
sir.
One second. Any specific reason for using photonic crystal for bending sensor? Yeah, already it's no. It's a bending sensors. Photonic crystal fiber is a high decent flexibility. It's the main reason for most of the fields are using photonic crystal fibers in bending applications. And also it is easily accurate, very minimum damaging level also. It's okay for you? Thank you, thank you. So any other question? Thank you, thank you.
Uh, yes, sir. Let me conclude the session, sir.
Yeah, please come to conclusion.
When educating the minds of our youth, we must not forget to educate their heart. In this way, now I like to call upon Mrs. T. Benishtina, Assistant Professor, Department of ECE of Cognado College of Engineering and Technology, to deliver a vote of thanks in this occasion. Please, ma'am.
Gratitude is the fairest blossom which springs the soul. It's my pleasure to propose vote of thanks on this online seminar sponsored by the Department of Biotechnology, organized by the Department of ECE on the topic Biotechnological Applications Using Fiber Optic Sensors. First of all, I would like to thank the Department of Biotechnology for sponsoring this seminar. I would like to thank Dr. P.S.K. Periyasamy sir, Chairman sir of Kongunadu Institution. I would like to show my gratitude to Dr. R. Ashokan sir, Principal, Kongunadu College of Engineering and Technology. Thank you, sir. Also, I would like to thank Dr. J. Yogapriya ma'am, Dean R&D. Thank you, ma'am. And I would like to thank Dr. M. Dharmalingam sir, Head of EC Department. Thank you, sir. And I would like to extend my sincere gratitude to our chief guest, Dr. N. Ayanar sir, for giving away a talk on fiber-based biosensors and its application. Thank you, sir. You have enriched us more on the fiber-based biosensors. Also, I would like to thank all the department HODs, faculties, participants, and the budding engineers. Thank you all.
Thank you, participants.
Thank you, sir. Participants, the sessions
Shall I leave
attendance
you?
come. Yes, sir. Yes. Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir. Participants, the feedback is being posted in the chat box. We'll give you 10 minutes. You can post your feedback for session 2. The participants who has filled the feedback form for session 1 and 2 will be getting the certificates within 2 working days. Thank you all.
Thank you, ma'am. And I once again like to thank everyone in this meeting for actively participated in the DPT sponsored one-day online seminar on biotechnological applications using a fiber optic sensor organized by Department of Electronics and Communication Engineering, Kongunadu College of Engineering and Technology. Thank you all.